Welcome, ladies and gentlemen. Section 7.6 has us solving what are called radical equations. These are equations that contain radicals, square roots, cube roots, fourth roots, etc., etc. The first thing what we like to do here is for step number one in solving these types of equations is we like to isolate the radical on one side of the equation. Eliminate the radical by raising both sides of our equation to an appropriate power. Now, what does this mean, appropriate power? Power, we then solve the resultant equation. For the variable. Now, this might be just a linear equation, or at times it could be like a quadratic equation. So, last but not least, we need to check any answer or answers back into the original equation. For even root equations. Now, you do not have to check your answer or answers for odd root equations, but if your equation has like a square root in it, or a fourth root, or a sixth root, you have to check your answers back out in the original equation. Reason being is because when you square both sides of an equation, sometimes you can generate false solutions. Okay, so in general, these are the steps that we pursue to solve radical equations in section 7.6. Now, I'm going to demonstrate several of these here. All right, so the first one we're going to look at is the square root of 3x plus 4 equal to 5. We're going to solve this radical equation here for x. First of all, we want to isolate any square root or radical on one side of our equation. Well, we already have that luxury. We have the square root isolated on the left side. Being the case, now what I'm going to do is I'm going to square both sides of this equation. When you square a square root, it disappears. And the left side simplifies to this. The right side goes to 25. And now we just simply solve this simple first degree equation. We subtract 4 from both sides. Divide both sides by 3, and we get a solution of 7. Now, it's very important to check your answer out because we did have an even root equation. We got a square root in this equation. So we're going to take 7, we're going to substitute it back into the original equation for x, and we're going to verify whether or not it satisfies the equation. So, is the square root of 3 times 7 plus 4, is that equal to 5? Well, the square root of 3 times 7 is 21. 21 plus 4 is 25. So is the square root of 25 equal to 5? And it does check out. So therefore, we will retain 7 as the only solution to this radical or square root equation here. So that equation is done. All right, let's try another one here. We are going to solve this square root equation. We have the square root of 4t minus 7 equal to -3. First of all, we want to isolate the square root on one side of our equation. Well, the good news is we already have it isolated. So we're now going to square both sides of this equation. But we also have the square of the right side. Now, when you square the left side, the square root and the square disappear since they're inverse operations of each other. And what results is 14 minus 7. On the right side, -3 times -3 is 9. Solving for t now, we add 7 to both sides. Divide both sides of the equation by 4. And therefore, we get t is equal to +4. Now we need to check our answer because our equation did have an even root in it. It does have a square root. So we're going to put 4 back into the original equation for t, and we're going to see if 4 satisfies the equation. So is the square root of 4 times, in for t goes 4, 4 minus 7, is that equal to -3? Well, 4 times 4 is 16, and therefore we're going to have the square root of 16 minus 7. Is that equal to -3? 16 minus 7 is 9. Is the square root of 9 equal to -3? And the answer is no, because the square root of 9 is 3, and 3 does not equal -3. So therefore, in the process of squaring both sides of this radical equation to solve for t, we generated a false solution. Sometimes those solutions are called extraneous solutions. And therefore, we have to toss out -3. Or excuse me, we have to toss out +4 as being our solution. So 4 cannot remain as a solution because it simply does not check out in our original equation back up here. So therefore, we would conclude that this equation has no solution. So there is no solution to that square root or radical equation. All right, let's try another one. Let's solve the square root of 5x minus 1 plus 3 equals 7. We will solve this radical or square root equation for the variable x. First of all, we want to isolate the square root on one side of our equation. We can achieve that by subtracting 3 from both sides. Now, to get rid of the square root, we have to square the left side. But if we square the left side of our equation, we also have to square the right side. When you square a square root, both the square and square root disappears, and the left side simplifies to 5x minus 1. The right side becomes 16. Now we just solve for x. So we just add 1 to both sides. We're going to divide both sides by 5 rather. And we discover that our tentative solution x is going to be 17/5. Well, ladies and gentlemen, we have got to check our answer back in our original equation because we do have an even root in our equation. We got a square root. So whenever you have even roots in a radical equation, you always have to check your answer or answers back into the original equation and make sure that they do check out. So I'm going to take 17/5. I'm going to replace x up here with 17/5, and we're going to verify, is 17/5 a solution? So the square root of 5 times x being replaced with 17/5 minus 1 plus 3, is that equal to 7? Well, 5 over 1 times 17 over 5, the 5's cross reduce out to 1, and we're left with 17. And we have the square root of 17 minus 1 plus 3. Is that equal to 7? Square root of 17 minus 1 is the square root of 16. The square root of 16 plus 3. Is that equal to 7? Well, the square root of 16 is 4. Is 4 plus 3 equal to 7? And it does indeed check out. So therefore, we will retain 17/5 as being the only solution, excuse me, to this radical or square root equation. So 17/5 is the solution to this equation. Okay, let's solve another one here. All right, we're going to try to solve this square root or radical equation for the variable t. Notice we do have the square root isolated on one side of our equation. Because of that, we can take the square root of both sides of our equation to eliminate this radical on the right side. Well, I'm sorry, we got to square both sides of our equation to eliminate this radical on the right side. So I'm going to square the left side of the equation, and I'm going to square the right side of my equation. Now, squaring the left side is going to involve taking t plus 5 and multiplying it by itself, in which case we're going to have to tap into the FOIL algorithm we learned in the past for multiplying binomials together. The right side is much easier to simplify. It simply simplifies the t plus 7 because the square of a square root gets rid of the square root and also gets rid of the square. So the right side is t plus 7. So the left side, we have some work to do. We got to FOIL this out. T times t squared. Multiplying the outer terms together, t times 5 is 5t. Plus, multiplying the inner terms together, 5 times t is 5t. Plus, multiplying the last terms of these binomials together, 5 times 5 is 25. Combining the two middle linear like terms here, 5t plus 5t nets us 10t. Now, this is a quadratic or second degree equation. To solve this equation, we're going to have to zero the equation out. So therefore, I'm going to have to subtract t from both sides and also subtract 7 from both sides. Therefore, our equation becomes t squared. Now, 10t minus t or minus 1t is just 9t. 25 minus 7 is 18. And the right side of our equation goes to 0. To solve this quadratic equation, we're going to try to factor this trinomial on the left side. We need a couple of factors of 18 that sum up to positive 9, the middle coefficient. After some thought, the only factors of 18 that work are going to be 3 and 6. So this trinomial immediately factors into t plus 3 times t plus 6. We now set both linear factors equal to 0. And we have to solve these variable factors for t. Solving this equation for t by minusing 3 from both sides, we get t is equal to negative 3. Subtracting 6 from both sides here, we get another possible solution as being t is equal to negative 6. Since our equation had an even root in it, a square root, we must check both these answers in the original equation and make sure they check out before we add them to our solution set. So here we go. We're going to check out t equals negative 3. So I'm going to take negative 3, substitute it in for t here, and see if it verifies or satisfies this equation. So is negative 3 plus 5, is that equal to the square root of negative 3 plus 7? Negative 3 plus 5 is 2. So is 2 equal to the square root of negative 3 plus 7, negative 3 plus 7 being 4? And we can see that, yes, it does check out. The square root of 4 is indeed equal to 2. So t equals negative 3 will be retained as one of our solutions to this radical or square root equation. We also have to check out negative 6 now. So let's see if negative 6 is a solution to the original equation. Take negative 6, substitute it in for t throughout, and then verify. So is negative 6 plus 5, is that equal to the square root of negative 6 plus 7? Negative 6 plus 5 is negative 1. So is negative 1 equal to the square root of negative 6 plus 7, which is positive 1? Well, is negative 1 equal to the square root of 1? But the square root of 1 is 1. And negative 1 does not equal 1. So therefore, it appears that negative 6 is not working. It's not a solution to the original equation, so we must toss it out. So the only solution to this radical equation would be t is equal to negative 3. So t equals negative 3 is the only solution to this square root or radical equation. All right, here's another one. We're going to try to solve this square root or radical equation for the variable w. To do so, we want to isolate our square root on one side of our equation. Now, we do not have it isolated on the right side, but we do have it isolated on the left side. That's good enough to square both sides initially. So I'm going to square the left side of the equation. And I'm going to square the right side of the equation. You got to square the whole right side. The left side trivially simplifies down to just w minus 3. Because when you square a square root, the square root and square disappear. The right side is not so trivial to simplify. It is not as simple as saying it's the square root of w squared minus 3 squared. That would be an error. No, on the right side, we're going to have to actually FOIL this all out. So here we go. The square root of w times the square root of w. And then we got the square root of w times negative 3, which is minus 3 times the square root of w. And then I got negative 3 times the square root of w is another minus 3 square root of w. And then I got negative 3 times negative 3, which is going to be this right here. So we got w minus 3 is equal to the square root of w times the square root of w is the square root of w squared. These are like radicals that need to be combined. A negative 3 square root of w minus 3 square root of w is going to net us negative 6 square root of w. Negative 3 times negative 3 at the end is a plus 9. The square root of w squared simplifies down to w. All right, now what we need to do is try to isolate the square root on the right side of our equation by dragging everything over to the left side, as we will prepare to square both sides one more time. So to do that, I'm going to have to bring this w over to the left side by subtracting w from both sides. And then I'm going to also have to bring the 9 over to the left side of the equation by subtracting 9 from both sides. W drops out on the left side of our equation to 0, and negative 3 minus 9 add up to negative 12. The w's drop out on the right, the 9's drop out on the right, leaving us with negative 6 times the square root of w. Now, what I can do is I can square both sides of my equation now to get rid of this remaining square root here. So I will square the left side and square the right side of this equation. The left side becomes just positive 144, negative 12 times negative 12. And the right side is going to be negative 6 squared of w times itself. So we have 144 is equal to negative 6 times negative 6 is 36. And the square root of w times the square root of w is the square root of w squared, which is just w. Finally, solving for w here, I divide both sides of my equation by 36. And therefore, we discover that 144 divided by 36 nets us 4. So w is equal to 4. Now we have to check our answer back into our original equation, because our original equation does have even roots in it, does have square roots. So we're going to check our answer out here. We're going to check out w equals 4. So I'm going to replace w here with 4 and replace this with 4. So is the square root of 4, is the square root of 4 minus 3 equal to the square root of 4 minus 3? Square root of 4 minus 3 is the square root of 1. Is the square root of 1 equal to, no, the square root of 4 is 2. So is the square root of 1 equal to 2 minus 3? But the square root of 1 is 1, and 2 minus 3 is negative 1. But guess what? 1 does not equal negative 1. So 4 simply does not check out in this equation. So we have to toss it out as a solution. And so, ladies and gentlemen, we would conclude that this radical equation has no solution. There's no solution to that equation. Now, in your spare time, I want you to look at example 6 in your textbook. I want you just to walk down through the steps that your author is illustrating for this particular example. All right, I'm going to solve one here that does require quite a bit of time to solve. It's probably the most difficult radical equation that you will have to deal with. We're going to solve this equation for x. It is an even root equation. Notice I do have a square root isolated on the left side of my equation. That's good enough to immediately square both sides of the equation. So we will do that. We'll square the left side, and we got to square the whole right side of our equation also. The left side trivially just becomes x plus 1. But the right side is in need of multiplying this all out. So here we go. Now the square root of x plus 2 times the square root of x plus 2 is going to be the square root of x plus 2 times x plus 2, which is the square root of x plus 2 squared. The square root of x plus 2 times -1 way over here is -1 times the square root of x plus 2. Multiplying the inner terms together, -1 times the square root of x plus 2 is another -1 square root of x plus 2. And -1 times -1 is +1. Now the square root of x plus 2 squared is just going to be x plus 2. These are like radicals and need to be combined. So -1 of these square roots of x plus 2, subtracting one more of these square roots of x plus 2, nets us -2 of these square roots of x plus 2. And we got the +1 at the end here. What I'm going to do now is try to isolate this square root on the right side of my equation. First of all, I'm going to combine my like constant terms on the right side. 2 plus 1 add up to 3 here. Now I'm going to move the x over to the left side by subtracting x from both sides of the equation, and also move the 3 over to the left side of my equation by minusing 3 from both sides. The x's drop out on the left, and 1 minus 3 nets us -2. The x's drop out on the right, the 3's drop out on the right. We're left with -2 times the square root of x plus 2. And now, what I'm going to do is I'm going to get rid of this square root on the right side of my equation by squaring both sides of my equation yet again. The left side becomes +4. The right side has us taking -2 and squaring -2. -2 times -2 is a +4. And the square root of x plus 2 squared is just going to net us x plus 2. So we got our equation down to this. Distributing the 4 inside the parentheses here. Now we just solve for x. So we're going to subtract 8 from both sides. We get -4 is equal to 4x. Divide both sides by 4. And we get -1 is equal to x. Okay. Now we need to check our answer back in our original equation because we did solve an even root equation. So we're going to check out -1. So take -1, substitute it back in here for x, and see if it satisfies this equation. So is the square root of -1 plus 1 equal to the square root of -1 plus 2 minus 1? This is a square root of 0. Is the square root of 0 equal to, this is a square root of +1. Square root of 0 is 0. Is 0 equal to, the square root of 1 is 1. Is 0 equal to 1 minus 1? And the answer is yes. So the only solution to this radical or square root equation is x equals -1, and we're done. All right, now this next radical equation is not going to be a square root equation. This is going to be a cubed root equation, but nonetheless, it still is a radical equation because it's an equation that contains a radical. So we're going to try to solve this cubed root equation for x. To do so, first I want to isolate my radical on one side of my equation. Well, the good news is I already have it isolated. So the next thing I need to do is get rid of this cubed root by cubing the left side of my equation. But if I cube the left side, I must also cube the right side. Cubing a cubed root makes the cubed root and the cube go away, so the left side simply becomes 4x plus 5. The right side is 3 times 3 times 3, which is 27. Solving for x now by subtracting 5 from both sides, I get 4x is equal to 22. Dividing both sides of the equation by 4, I get x is equal to 22/4, which reduces down by 2 down to 11/2. Now, ladies and gentlemen, you do not have to check your answer back in your original equation because this is an odd root equation. It's a cubed root equation, not a square root equation. So you do not have to check your answer. That is your solution, and we are done with that problem. Now, this next equation here may not initially look like a radical equation because it has a rational exponent. But ladies and gentlemen, we determined or learned earlier in this course that a rational exponent really is a radical. And so therefore, this is a radical equation since x plus 3 is raised to a rational exponent here. And so how are we going to, solve this equation? Well, first of all, what we could do is write the left side in radical form. That's to say x plus 3 to the 2/3 power is like taking the cubed root of x plus 3 squared. So to solve this equation now for x, we're going to have to get rid of a cubed root, and we do so by cubing both sides of our equation. So therefore, I will cube the left side of my equation, and I also have to cube the right side. When you cube a cubed root, the cubed root and cube disappear, and the left side just simplifies to x plus 3 quantity squared. On the right side, we have 4 cubed, which is 4 times 4 times 4. 4 times 4 being 16, 16 times 4 being 64. All right, now we need to solve this quadratic equation here. And we could FOIL out the left side here, x plus 3 times x plus 3. So x times x is x squared. X times 3 is plus 3x. Multiplying the inner terms together, 3 times x is plus another 3x. And 3 times 3 is plus 9. Combining the like terms in the middle, we get x squared plus 6x plus 9 equals 64. We're now going to have to zero this equation out by subtracting 64 from both sides of the equation. Hence, we get x squared plus 6x minus, 55, I believe. Now we want to factor this trinomial. We need two factors of negative 55 to sum up the middle coefficient of positive 6. After some thought, it's going to be a positive 11 and a negative 5. Therefore, this trinomial factors in x plus 11 times x minus 5. Setting both variable factors equal to 0 and then solving for x, we get our potential solutions. One solution is being a negative 11 and the other one is being a positive 5. Now, ladies and gentlemen, this was a cubed root equation. Because it's a cubed root equation, we do not have to check our answer back into our original equation, because this is really a cubed root equation, not a square root equation. And so we have two solutions, and there they are, negative 11 and positive 5. Okay, so I have demonstrated several examples of solving radical equations. Most of them were square root equations, but then we started getting into cubed root equations. By having seen these examples and studying through these examples, and also looking at example 6 in your textbook, you should be ready for the homework for section 7.6.